Hello, I'm Ryan Nelson from Rigaku, and Akalish already covered some very important points that he's looking at phases, and XRF looks at the composition, so we complement each other. So we're going to cover the principle, qualitative analysis. We're going to try to optimize settings and hardware conditions, anyone using WD, quantitative analysis, statistics, sample prep, and applications. So the principle, we're looking at a very narrow range of wavelengths and proportional to energy. It's typically very shallow, maybe a half micron to about a half millimeter in depth. And that's typically what we're looking at in an electromagnetic spectrum. And the main point is when you're selecting anode material is you're going to have characteristic lines and you're going to have the continuum. So most of the characteristic lines will be in the middle of the periodic chart, be rhodium, palladium, and moly, and tungsten, and then chrome for light elements. So most of the machines will use rhodium. This is very efficient with the edges and exciting the other elements in the periodic chart. You also have the rhodium L lines you have to consider for light element analysis. So both of those would be a consideration when you're selecting the system to analyze your materials. And what's going on is we have the characteristic X-ray and electrons impacting the anode material and generating the primary beam characteristic, and then the continuum from that. And the interactions with the material, of course, is heat transmitted, and then you have scattered and Compton scatter based on the average atomic number, photoelectron, and then fluorescent, which is typically only 0.3%. So most of it is heat. Some of the machines, the higher power machines, will heat samples to 80 degrees, 30 to 80 degrees. So if you have a sensitive material, you have to think about that when you're in the machine measuring. Most of the throughput is 3 minutes to 10 minutes. So if it was in there 30 minutes, could get that to 80 degrees. So that's a consideration. And also escape depth. If we're looking at something, for example, in this example, we have cadmium and iron, 200 micron and 60 micron, but in the light element matrix, you can see the depth is 4 millimeter. So when we're calibrating, we try to maintain a constant thickness. We're setting up at a constant weight, because all of that can be taken out in the calibrations. In a qualitative analysis, you have to input all of this information in order to get accurate results. Differences between the machines, of course. People may have ED based on budget and may have WD, but it's really resolution and LDL and detection limits. So in principle, of course, you have the primary beam passing through a filter, and then fluorescent X-ray secondary passing through a collimated slit to generate a parallel beam, scattering off of a crystal with a certain spacing, and then rotating in theta. And 2 theta is your detector array. So that follows that, typically maybe 2 to 95 2 theta. And analyzing crystals that typically you find in the machine would be lithium for heavy element, and PET and germanium and other even curved crystals for some of the light elements. For sulfur, we may use an RX9 crystal. And then, of course, the ED comparison is it's simultaneous, and this is sequential. And so we collect all of this, but at maybe 120 EV versus WD with a much higher resolution. Advantages, of course, rapid analysis, 10 to 20, up to 3 to say 8 minutes for 10 elements. It's non-destructive. Sample preparation, we can look at solids, powder, liquid samples, can be analyzed, can be either top down or bottom up. We have special cups for that. And it's not affected by a chemical state. Again, we're looking at the composition versus XRD. And it's very precise. Beryllium, of course, lighter elements, there's more deviation versus it's based on square root of count rates over counts. And qualitative analysis using a theoretical library lookup. So that's very good typically to ICP referee methods. And quantitative, of course, is based on empirical setup and FP setup. So the empirical setup is whatever values you put in, you'll generate a plotted line. And FP will use automated FP corrections and influence coefficient corrections. And you'll end up also very accurate analysis. And also thickness can be measured in most machines, usually up to about 10 layers from those products. Types, okay, again, it's based on cost, but we have one back there, a DE, and that's 16 watt. So that's very good for portability and measuring everything from aluminum up through uranium. And it's a portable SDD, its resolution and throughput. And then we move up to bench and floor 4 kilowatt. And we're typically looking at 3 to 8 minutes and 10 seconds on the simultaneous. So again, it depends on what you need in your production, your SOP, to make decisions on sample handling or if you need throughput at high precision. Qualitative, what are the key points? Now this would be using a lookup library. It would be theoretical known calculations and count rates from a 30 to 60 element library. And you use a FP model to calculate the results. And you have to declare all of the material to the machine and all of the elements present. And it automatically will insert filters and everything else and correct for the absorption and enhancement. So that in many, many evaluations has proven itself to be quite accurate. The problem that typically occurs is people have assumptions in SOP and the FP, which is based on the math, doesn't correlate. So it's very useful to try to correlate the qualitative to your quantitative setups initially, determine if you're going in the right direction. Techniques, of course, balance components. So is it organic? Does it have a loss on ignition? Does it have carbonates you drive off as CO2? Is there scatter in the prep of the material, which will affect the background scatter? Fixed concentrations for knowns. Can you match it to a library reference and improve your accuracy? And then other corrections employed for your flux binder dilutions, your atmosphere absorption, your film and impurities all have to be corrected for. And then changing and converting back and forth between elemental and oxide. And of course, K alpha and K beta lines are deep, and the L lines less so, and M lines are surface so. Which line does not have overlap? Which line does not have some influence of near an absorption edge of another element? And what model should you use? Now, most of the machines will set up their all of the conditions for you, but sometimes when you're setting up empirical calibrations, you'll have to make decisions on what's the best model. So quantitative, standards. So you need, degrees of freedom always comes up. A lot of companies will use one standard, fit to the origin, which is incorrect, but they will. 3 standards, and even 5, but even with 5 standards, you really only can use slope and offset. You can't apply any corrections. When you get up to around 9 or 10 standards, there's enough math where you can apply maybe 2 or 3 corrections to it in an influence. And the people who wrote all the algorithms, et cetera, suggest 30 to 60 standards are ideal for very good math. So that's the typical calibration range. You have to be concerned with grain size and homogeneity. We want 40 micron and less. 40 micron yields a uniform count rate and sufficient sample thickness. So most machines will estimate that for you. But if you had variable sample thickness with a high energy element like zirconium or moly, you'll get the thickness influencing the count rate, which is incorrect. So if it's constant again, you won't have a problem, but you have to be aware of all of these things when you're calibrating in a quantitative application. And then setting the conditions. So you can do this manually, or most of the machines will use something, we call it guidance, that will set the conditions for you. Background points, PHA, count times, and estimating the analyzing depth, which is very important. And then the influence. So you can run all of your calibrations with no corrections for influence, but you'll probably end up with quite a bit of error as a result because you can get enhancement. Any other higher energy element can refluoresce material in the matrix, and anything near an absorption edge can absorb other materials depending whether it's on one side of the edge or the other, or enhance it. So you have to declare all of the elements typically or know enough that they don't have an influence on overlapping elements. And of course, in cements, you can put in, we don't do the phase analysis, but we could put in bow calculations, give you some of the phase characteristics in the system. Power mask, tube current, right? So it's directly proportional, power to intensity yield. And here's an example of silicon, right? So you can see as we go up, we're getting more counts. And also mask diaphragm. So we have mask and diaphragm sizes in the machine. Depends on your sample size. And you see that that's proportional, 35 or 30. So you have to make a decision on the mask area versus the count rate you need, square root of count rate over counts for your precision estimate, your LDL. Now the system will do that for you, but you have to make all of these decisions on what you're going to use in sample area and the other hardware characteristics. Filters are in all the machines typically. Depending on what anode you've selected, you'll be using a nickel or a zirconium to remove those tube lines. Obviously, you can't do any catalyst work without these filters in place. So this would remove all those characteristic lines. The other filters by absorption edge reduce the noise level of your elements of interest. So people looking at catalysts or strontium or other moly, barium, etc., with other elements will need to employ filters. And then the slit for collimating, right? So you can see an example here, chrome and manganese. So we can remove the overlap effect by changing the slit from an S2 to an S4. So we don't have a net contribution to the count rate here by just changing the slit and higher resolution. Crystals, again, depending on the D spacing, right? This is a typical example of a lithium 200 versus 220. We can separate the peaks, and we don't have to worry about overlap in that case. So the other caveat to that is, with a higher resolution crystal, you lose intensity. So it's showing 15 versus 70. And count rates using different crystals. For example, this would be looking at fluorine. We can increase 180 versus 20 with different crystals. But of course, all of this has to be known when you have an application and what hardware is required, what crystals are required. You have to know all of that and then end up with a template for your system. PHA and background, so this is some of the settings. Of course, this is a slope, typical slope or horizontal. You'll have to select two backgrounds for intersect with the net. Typical setup in the software. So what you do in any case when you're optimizing something is backgrounds for trace, peak angle, and overlaps, and time. So that's true for any X-ray. So all of this is automated in most systems. So this will give you the best accuracy down to trace level measurement. In PHA, a lot of the machines may not have this, but PHA pulse height analysis is a special circuit analysis looking at the individual pulses, and you can separate overlaps using this method. So you can move the PHA window left, right, and exclude overlap elements like tin and lead and other elements like that. And also increase your counts by moving the gate to the left and right. And you can estimate your precision. So it's very important before you commit to an 8-hour calibration that you know what time will yield your SOP LDL and your throughput. So you can use this, uses this formula here, and you can estimate all of your conditions for your setup. Atmosphere, vacuum versus heavy. Of course, everyone knows vacuum, not much effect with transition elements and heavy elements. But vacuum for light elements is critical. You can see there's no difference between vacuum and helium here between the total count rates. But looking here at light, of course, there is a big difference. Of course, you can't use vacuum typically with powders. You can with special applications. But this would be a difference, of course, the count rates from 80 to 90,000 counts. Other optimizing, right? Analyzing depth considerations, for example, looking at copper, iron, etc. Organic matrix, very deep, 3.7 millimeter. And then less, of course, as you go up in atomic number. So as you're looking at in metals, etc., it's very shallow, but you can get very deep, up 60 in an organic for cadmium. So you have to think about that when you're preparing your samples and for the depth. Most people use a 5 millimeter depth on their samples. And overlaps. So you'll see a lot of things here in minerals, etc., that are present. This would be corrected with PHA adjustments. That's why I mentioned that earlier. So you can eliminate any of these other elements, overlap with your elements of interest here, using the PHA adjustment in your quant. Calibration, using guidance. So you're calibrating, you have a flow wizard. You just go right down the flow chart. Very easy. Step through, sets it up, and you're ready to go with the FP. Then, of course, we have the peaks that we count and gather the count rates, KCPS, and it puts it into the final plot. In this final plot, of course, we have this matrix consideration. This is your typical raw data. And if you use an automated FP calculation, you'll end up with a plot like this. Or with empirical, you're going to be using your own inputs for matrix influence and absorption. And you're looking for this as an ideal, right? Typically, you end up with this. You can see it's 1.7 versus 0.03 with FP, automatic calibration. Statistics. So most of the error, of course, is not the stability. It's definitely going to be count loss and really sample setup. So errors, this is typically the contribution to errors. Seen this many times. Grain size mixing. So if you mix 40 with 170 or 220 micron, you'll end up with two intensity distributions. Homogeneity. So you may have precipitation. You may have a gradient in your sample prep. Surface roughness, 40 micron versus 270, or 180 grit versus 400 grit polishing, will end up with a count rate change. Whether it's wet. Of course, if it's hygroscopic, it'll take up water on the surface, which will affect your X-ray beam. Coexisting elements, line overlap, and of course, errors in the chemical values.
The microphone. Oh, hold it.
Too much mumbling?
Yeah.
Okay, sorry. Sample matrix corrections. So employing all of these is generally up to you. Some are automated. Liquid film in the atmosphere, weight volume because it's mass per unit area. Powder, grain size again I mentioned, weight, LOI, pellet, fused bead, flux ratio of the material, which you can correct for a sample to sample. Whether it was oxidized, gain on ignition and loss on ignition. Film, substrate, and layers, you're going to have a transmitted component and absorbed component. Matching, qualitative to improve accuracy. And inputting a balance and scatter. Because you can use scatter estimation, Compton scatter, based on the average atomic number, to calculate the light element composition, be it CH2 in an oil or in fuel. Typical effect of course, particle size. 40 micron is ideal. And of course, larger particles, you get absorption and scatter, right? So you want a very fine particle distribution. Surface roughness, you can see it does have some effect. This is relative to 1, but different grid sizes, you'll end up with a distribution in count rates from 50 to 240. So that can have an effect looking at traces or other elements when you're preparing metal samples. Also, when you're preparing powder samples, etc., the grinding time and precision, right? So typically 4 minutes and 20 tons to 30 tons is ideal for pellet samples. And this is just an example of polishing. Go through that. And sample preparation, right? Mixing with a binder. So typically high silica don't require it, but if you have to add a binder, it's usually 10%, 10 to 30%, and that's compensated for in software. And then 20 tons as far as compression. And we typically use a cylinder dye. We can also look at trace contaminant levels in a boric acid medium in a well, or we can look at that in a binder, a cellulose binder, so we can make small analytical wells, deposit our material, and look at trace materials that way using this method. Small amount of powder using sample boards, same thing. We can also use a boric acid backing. So if you don't have enough material, you can bring it up to a certain level with a boric acid backing. It doesn't have any signal. So we often use that. And again, looking at trace materials. Fusion, I don't think anyone's doing that. No. Okay, that gets rid of the mineralogical effect. So if you fuse the material, you don't have any of the influence of the other elements or the mineral size. Liquid analysis, so whether it's top down or bottom up, you can use a float cell for top down, and you can use a standard cell for bottom up. One thing you have to be wary of course, with sulfur material, if you're looking at fuels, is a sublimate, and you'll end up with a sulfur contaminant in your machine if you should leave it in there. So there's some material you have to be a little careful with handling. And then also liquid by droplet. They're called filter membranes or ultra-carry, micro-carry. So you can do it down to 50 ppb of most of your analytes using this method. So it's 250 microliter aliquots deposited in the center of a hydrophobic membrane and then analyzed in the machine. And it'll give you pretty good accuracy down to 50 ppb or 10 ppm. Also another new method is oil solidification. So there's always an issue with precipitation, etc. So we end up with a solidification material at about 80 to 120 degrees, and we solidify the material, be it an oil or grease. Then we can analyze under vacuum, get very good results for a light element using this method. Also mapping examples. It's not the same as pixel mapping with SEM, but we can do heat maps and 3D. So we're looking at materials, looking at something in a sample. You can embed it in a boric acid medium or in a well, and then get a 2D and 3D map of the different materials. And this is thin film analysis showing the saturation. Applications. Okay, everything you can imagine. Of course, even organic material we can do. Most of the work we're looking at here is chemical and petrochemical. So sulfur, etc., wear metals, looking at mineral materials, and soils, etc., and everything else. Looking at alloy, here's typical results from an alloy measurement and setup and accuracy down to 77, 97. So it's a 3 kilowatt system. So it's very complicated to set this up, but there are some methods that we use now. Oil solidification, also I'll discuss in a minute, pre-calibration. So you don't have to set up the calibration, it's already optimized. Oil solidification results. So you can see here, liquid versus pellet, liquid air, and then pellet air is generally improved over the liquid because we don't have precipitation occurring and other issues with instability in the sample. Some of the other packages put in, so you don't have to set up everything, you don't need the expertise, is multi-method element analysis or pre-calibration packages. So they can end up with a range as just a kit. So the system's already set up for all oil analyses you may be performing. And it employs these corrections for geometry and film, absorption, and overlap automatically. Then you end up with a pretty good value in ppm here. Without and with, you can see the difference in accuracy. So very good with, without, very poor. So that's usually required. Oil matrix again, very good. Heavy oil, diesel, gasoline. Repeatability, it's also very good. Okay, looking at sulfur. Okay, the D2622, so we're getting down to 10 and 5 ppm, so we really need a WD system. So most of the bench top and floor models will handle this level of accuracy. Also, some internal standard methods with lead, with bismuth for lead correction. And you can see, of course, we have capability in ppm down to 0.3 ppm for this sample. So very good with a curved crystal. So pretty good results there. Catalyst, of course, that's on the characteristic lines of the tube. So we need the filter to remove that, right? Another application. Cements, of course, very well understood with the bulk calculations. So a 2 kilowatt typical range, accuracy. Of course, that has to follow the C114 spec. And then trace is also another built-in package that can do this type of application. Now looking at your rocks, I'm not an expert geologist, so grabbed a few things, but you can map, right, which we had already looked at. Also, there's many apps generated for this kind of analysis. And here's typical summary results, looking at biotite and looking at iron and high silicon and quartz. You can see very good results because you can get down to 0.5 millimeter with the machine. So you can look at these individual spots of interest on your sample. Drilling mud, right? More calibration packages. So this is typically what you can get in a machine. They'll be auto set up. You'll get a kit and you can perform these analyses without a lot of input. It's already set up for you. And cement, again, reference accuracy. And more correlation with and without correction for oil and wear metals. And the oil matrix film correction, filter concentration, PPB results for various elements in ppm. Of course, we have all of this. I know I went over all of this, and I don't know if anyone's using WD or XRF, but I hope this may have helped a little bit. But we, of course, have all that expertise, so if you have any questions, you would call us and we'd set up all of your hardware parameters and everything else. Okay? Thanks.